Hi, in this video, I'm going to go through the OCR AS level chemistry paper, and this is paper one. Okay, paper one, and I'll do this in two halves. The first half in this video, and continue in the next video. Right, so on to the multiple choice section. Question one: which compound has the highest boiling point? Right. So ethanol is ethanol and heptane and water are all small covalent molecules, and so you're going to get only going to get intermolecular forces between them. So they're going to have lowest boiling points. Heptanes will be lowest of all because it's only got London forces. There's no polar bonds in it. Ethanol and water will be a bit higher because you've got hydrogen bonds. But the answer to this one, the highest boiling point, is going to be sodium chloride because this is a giant ionic lattice. Okay, it's going to have a very high boiling point because of the strong electrostatic attractions between the positive sodium ions and the negative chloride ions. So it's going to be way higher than the others. Okay, we've got the Pauling electronegativity values for some elements in the periodic table there. Okay, so the higher the electronegativity, the better the thing is. The atom is attracting electrons towards itself in a covalent bond. Okay, so for example, if we had hydrogen, well, let's just look. We've got bromine chloride there. Chlorine is more electronegative, that's 3.16, so that's going to be delta minus, and bromine will be delta positive and slightly positive charge. So D is wrong. Okay. Right. Boron and chlorine. Well, boron, thanks for doing this one here. Boron and chlorine. Boron is a lot less electronegative than chlorine, so chlorine would have the delta minus there, not delta positive, so that's wrong. Carbon and fluorine. Well, fluorine is the most electronegative element, so that's always going to be delta minus, and it's not, it's delta plus here, so that's wrong. So this one must be the correct one, and it is, because nitrogen is a lot more electronegative than iodine. So nitrogen would have the delta minus on it. So A is the right answer there. Okay, which compound releases hydroxide ions when it dissolves in water? Well, most of those things there are acids. So that's ethanoic acid, it's a carboxylic acid. This is nitric acid, and this is sulfuric acid. They're all going to release H plus ions in water, aren't they? Or really H3O plus, yeah. Ammonia, NH3, right? That is basic, isn't it? The reason why it's basic, it is good at accepting protons. It's got a lone pair on the nitrogen. If you react that with water, it's going to remove an H plus from the water to form NH4 plus, leaving be the what if you remove an H plus from H2O, you end up with OH minus. So that will give us hydroxide ions. You should know that ammonia, when you dissolve it in water, it gives an alkaline solution. You've got OH minus ions there. Okay, which alkane is 82.8% carbon by mass? Well, let's do the first one. So the MR of methane is 16, sorry, and there's one carbon in it, so that weighs 12. So that is going to be 12 over 16 multiplied by 100, 75%. It's not that one. Let's do ethane. So that's going to be, right, ethane is MR of 30, and we've got two carbons in there. So 2 times 12, 24 over 30 times 100, that's 80%. So it's not that one. It's probably going to be C. You can see with hydrocarbons, as they get bigger, the proportion of the molecule made up by carbon actually increases. Okay. So let's have a look at C. So that's butane, which has got an MR of 58. There's 4 carbon atoms, so all times 12, 48 times 100. That gives you 82.74. So that's the one. Okay, this is the answer. If you do the same for D, you find out the percentage there is because it's a bigger molecule, is even lower. It is, so the percentage of carbon is even higher. That's about 84.2% for that one. Okay, so that's the answer to that one. Right, now there's a bit of a quick way of doing this, isn't it? Right, which sample has the greatest mass at RTP? Well, what is the volume of 1 mole at RTP? It's 24,000 centimeters cubed, isn't it? Okay, so how many moles have we got in 50 centimeters cubed of argon or of any gas? So moles is going to be equal to 50 over 24,000. The mass of argon, the mass is going to be the moles multiplied by the AR of argon, because it's an atom, it's not a molecule. So that's going to be 50 over 24,000 multiplied by the AR of argon, which is 40. Now we do B, let's do B, do that one. So we can do the same thing there. So the mass there of oxygen is going to be, what volume have we got? We've got 100 over 24,000 multiplied by the MR of oxygen, 2 times 16 for O2, that's 32. Right, now you can see we don't really have to work all of these out, because for all of those things, what we're going to be doing is we're going to be dividing by 24,000 every time, so we can cancel that out, can't we? Yeah. Okay. And also, instead of having 50 times 40, we can just say, let's do 0.5 times 40. Yeah. So that one is going to be 0.5 times 40, which is equal to 20 grams. This one is going to be, no, it's not 0.5, it's going to be 1 times 32 grams. This one is 150, so that's going to be not 1, but 1.5. Nitrogen is 14, so N2 is going to be 28. 1.5 times 28 is equal to 42 grams, so that's the most mass, I think. And do the last one, so 200, so that's going to be 2, and neon is only 11, so that makes 22 grams. So our answer is C. So you don't have to work out each one completely, because you're just comparing them all. Okay. Right. A student mixes some KOH with calcium hydroxide. Okay, what's the OH minus concentration in the resulting mixture? Now, it's important to realize here, when you dissolve 1 mole of calcium hydroxide, you're going to get 2 moles of OH minus ions. Okay, whereas with KOH, when you dissolve 1 mole of KOH, you only get 1 mole of OH minus ions. So let's first of all work out the moles of KOH. So moles KOH is equal to the concentration multiplied by the volume. So that's going to be 0.1 times 250, which is 0.25 in dm cubed. So 0.1 times 250, sorry, times 0.25, which is equal to 0.025. Now, because it's KOH, there's just 1 OH for in there. So moles of OH minus from that is equal to 0.025. Okay, now let's do for the calcium hydroxide. So the moles of calcium hydroxide, concentration times volume again. Concentration is 0.1, and we've got 750, so that's 0.75 in dm cubed. 0.1 times 0.75 is equal to 0.075. Right, so therefore the moles of OH minus for that, we've got to double that, because it's calcium is CaOH twice. So that's going to be 2 times 0.75, which is equal to 0.15. Okay, so now we've got to add these two together. That's going to be the total number of moles of OH minus. So total moles of OH minus 0.025 plus 0.15 is equal to 0.175. Now, the final thing we need to do now is that's the moles of OH minus. We need to find out the concentration of OH minus. So conc is equal to moles over the total volume. So the moles is 0.175. What's our total volume? Well, we mixed up 250 centimeters cubed with 750. That makes 1,000 centimeters cubed. So that's 1 dm cubed, which is divided by 1. So 0.175 moles per decimeter cubed is our answer, which is D. Okay, right, number 7. After delivering a solution from the pipette, a little droplet remains in the tip of the pipette. So when you're using the pipette, you've probably seen it. When you empty it, you always end up with a little bit left in there. Okay, now what you do is that you don't try and shake it out. That's all accounted for. So the answer is you leave the droplet in the tip, right? You don't have to do that. You don't shake it out and you don't force it out. Okay, you leave it in there. 7B is the answer. That's probably the worst drawing of a pipette that I've ever seen, so sorry about that. Right, ionization energies. Which sequence of elements has order increasing first ionization energy? Now, so we're looking across period 3 there, aren't we? You can see we've got sodium. We're looking at sodium, magnesium, aluminium, silicon, phosphorus, and so on. Right, now if you remember your little pattern of draw a little graph for it, you get, right, so for sodium it's low because it's coming from 1s, from 3s, sorry. For aluminium, it's going to be, for magnesium, sodium, for magnesium, it's going to be a bit higher because it's coming from 3s, but there's a bigger nuclear charge. Then it dips down a bit for aluminium, you remember, because it's coming from 3p now, not from 3s. It goes up. It goes up when you go to silicon. It's coming from 3p again, but of course, it's coming from, you've got a bigger nuclear charge. It goes even higher for phosphorus, because again, it's coming from 3p. And then for sulfur, you get a little dip, you remember, and that's due to pair repulsion. So you have to be careful with that, okay? So let's see which is increasing first ionization energy. So A, sodium goes up for magnesium, but it doesn't go up for aluminium. It goes down for aluminium. So that's wrong. Magnesium to aluminium, it goes down, so that's wrong straight away. Aluminium to silicon, it goes up. If you look at the diagram, yeah. And from silicon to phosphorus, it goes up. Yeah, so that's right. Let's have a look at the last one. Well, silicon to phosphorus, it goes up, but then it goes down a bit for sulfur because of the pair repulsion. So that one is wrong. So C is the correct answer there. And that little, and then if you carry on, you by the way, okay. And then, so that would be going up to neon. And then when you come down to potassium, of course, it drops right down again because you're going into a new quantum shell. So if you remember that little graph of first ionization energy, is really important, comes up a lot. Okay, which element has atoms with the largest number of unpaired electrons? Okay, unpaired p electrons, sorry. So aluminium, right, so if you look where aluminium is, it's here. So we can see aluminium is 3s2 3p1, so that's got 1 unpaired p electron. Oxygen is in period 2, so that's going to be 2s2 2p4. Now I have to be careful there because remember the 3p orbitals, right? How are the electrons arranged there? Well, they always have parallel spins if they can. Oxygen's got 4, so it has to pair up there. So the oxygen has got 2 unpaired electrons. Chlorine, well, that's 3s2 2p5 3p5, sorry. And again, if I just draw my p orbitals, so they're going to occupy like that, pair up because they've got 2. So you can see there you've only got 1 unpaired p electron there. And phosphorus, this is going to be a 3, I think. So that's going to be 3s2, 3p3. So that has got 3 electrons in the p orbitals, but each one's in a separate p orbital. They're not paired up, so that's got 3 unpaired electrons. So our answer is phosphorus. Right. 10. We've got the combustion of propane there, see, with oxygen, and it gives us delta HF values, and we've got to work out the enthalpy of combustion, which is this equation here. So we need to find out delta H for that equation. So how are we going to do that? Well, I've drawn Hessi's law cycle here. Now remember, so this is, we need to find out this delta H value here. When you're given delta HF values, you should always put down, as the third thing in the Hessi's law cycle, this is the elements in their standard states, okay? So not oxygen atoms or O2 molecules and hydrogen molecules and so on. Right, now on the red arrow, what we're doing, we're forming 1 mole of propane, and that's got a delta HF value of plus 20, so I'm going to write that down there. Nothing happens to the oxygen, so there's no enthalpy change there to worry about. Let's look for, on the other side, the green arrow, right? So what we're doing there, we're forming 3 moles of carbon dioxide. Each one of those is minus 394. And we're forming 3 moles of water, so that's 3 times minus 286. So if you add that lot up together, you get 2040. And delta H there, what's delta H equal to? Well, we are going against the red arrow here. So what do we do with that? We change the sign to minus 20. We are going with the green arrow. So that should be minus there. So we keep the sign, so it's minus 2040. So that gives us a total of minus 2060. Is that one of the options? It is that one there. Okay. By the way, you could rule out C and D straight away, couldn't you? Because they are positive values, yeah? That means endothermic. Burning things is never going to be endothermic, obviously. So they're definitely wrong. Okay. Right. 11. Right. We've got the Boltzmann curve. Okay. And it's showing a gas at 2 different temperatures. Which Boltzmann distribution shows the dotted line of the curve at a higher temperature? Well, let's have a look. What's going to happen? Well, we've got energy on this axis, yeah, and number of molecules. So when it gets hotter, the peak is going to shift to the right because the sort of average energy is going to go to the right. So on that basis, it's either got to be A or B, hasn't it? Because in C and D, the peak's going to the left, so they're definitely not right. Now, why is A correct? A is correct and B is incorrect because you can see here the height of the peak has got to be a little bit lower with a higher temperature. And the reason for that is because the area under the curve must stay the same under both curves, okay? Because that is proportional to the total number of molecules. And you haven't changed the number of molecules. So if you looked at B, B would be wrong because the area under the dotted curve is definitely bigger than the area than the other one, and it's got to be the same. So A is the right answer. Incidentally, let's just look at C and D. Well, which is the correct dotted curve for a lower temperature? Let's have a look at that. Which is the correct one there? Well, the correct one is D, yeah, for a lower temperature, because again, the area under the 2 curves has got to be the same. And you can see in C, the area under this continuous line is bigger than the dotted one, isn't it? Okay, so D is the right answer. If it was asking for lower temperature, which is not, so our right answer is A. Okay, Which statement about dynamic equilibrium is not correct? Right, a catalyst increases the rate of both the forward and the reverse directions by the same amount. That is correct. Dynamic equilibrium exists only in closed system. Yeah, that's true, because if you take the lid off something, then all the gases escape and it's not going to reach equilibrium. The concentrations of the reactants and products are equal. They're not equal. They don't change, but they're not the same as each other. Okay, so that's wrong. So C is our correct answer here. Let's just check D. The rate of the forward reaction is equal to the rate of the reverse reaction. That is true always when something's at equilibrium. Okay, so C is the answer we're looking for there. Right. What is the number of unsaturated isomers of C4H8? Now, unsaturated, now, of course, we could have cyclobutane, okay, is an isomer of C4H8, like that. But any cyclo compounds are not allowed because they wouldn't be unsaturated. There's no double bonds in them. So we can forget about all the cyclic things. We just have to worry about the ones with double bonds, okay? So let's have our 4 carbons in a row. Or we can put our double bond there. Okay, that's but1ene. Can that show Ez isomerism? Because it does tell us about stereoisomerism. It can't, because you can see there, look, we've got, on this end carbon, we've got 2 hydrogens. They're the same, so it doesn't matter which side they go on. So that's just going to give us 1 isomer there. Let's look at but2ene. Now, but2ene, can that exist as stereoisomers, as Ez isomers? Well, you can see it can, because look what we've got there. Attached to these 2 carbons, right, I've got a methyl group and an H. Okay, they're different. They're both different. And the same on the other side. I've got a methyl and an H. So that can exist as 2 Ez isomers. I'll put 2 down there. Right, what else can we have then? We could have, instead of having 4 in a row, we could have a branch, couldn't we? So let's do that. There's only 1 branch we can put there. Now let's where can we put the double bond? There. Right, now if I put the double bond in the blue position or the green position, you can see it's exactly the same thing. We're just sort of turning the molecule around, aren't we? So you can see there's only 1 possible isomer. Now let's see if that can exist as stereoisomers. And it can't, because again, we've got on this carbon here, we've got 2 identical groups, 2 hydrogens. So that will just give us 1. So the total is 4. Right, what do curly arrows always show in reaction mechanisms? Okay, right, so let's just an illustration here. Let's do nucleophilic substitution. Right, so here's bromoethane. Let's draw the mechanism here. We'd have, right, OH minus. Now what do we do there? We'd have this is a delta positive on this carbon. So we draw a curly arrow, those electrons. Now what, that's a lone pair of electrons. And then what would happen is a pair of electrons that would move there, and that's a bond pair. So is it movement of 1 electron? No, it's always pairs of electrons, isn't it? Is it a movement of a pair of electrons? It is always that. Is it always a movement of a lone pair? No, sometimes it's a bond pair. So that's not right. Is it the movement of electrons in a covalent bond? No, sometimes it's the lone pair. So the answer there is B. 15. Which structural isomer of C7H16 such has the weakest induced dipole-dipole London forces? Okay, now it's going to be the most branched molecule, isn't it? Because if you think, right, if you've got right, let's say you've got hexane, heptane, 1, 2, 3, 4, 5, 6, 7. Okay, so if you get another heptane molecule there, right, they can lots of points of contact. Okay, and you can get, okay, if it's got a branch in it though, if it's like this, well, you can see there's less possibility. The molecule's got less surface area, really, hasn't it? So which is the most, so the points of contact will be fewer and the London forces will be weaker. So which is the most branched? Well, this one here is 5 with two branches on it. This is just got one branch on it. This has got one branch on it, but this has got three branches on it. Okay, so you draw that out. You've got this butane, and you've got two methyl groups, one there, and another methyl group, one there. So it's very highly branched. So the surface area of the molecule is less, so there's less points of contact possible. So our answer would be D. That would have the weakest dipole-dipole interactions. So it would have the lowest boiling point as well, wouldn't it? Okay, which compound has the smallest bond angle? Okay, now you can see here we are the smallest bond angle you can have is you can have 90 degrees in some things, can't you? But there's in octahedral things you can have 90 degrees, but there's no octahedral things going on here because we've just got carbons, so we can forget about that. So the smallest bond angle we're going to have is when you've got a tetrahedral carbon. The bond angle is let's draw ethane there. Okay, so you can see that all the bond angles there, they're all going to be 109.5, aren't they? Okay, so we've got all of those compounds have got carbon in, so they're all going to have 109.5. Is there any that we could have smaller than that? Well, we could, if you get a lone pair somewhere, like for example in water, if you get a lone pair, well, let's do ammonia. In ammonia, you've got 3 bond pairs, and you've got 1 lone pair here. That's a lone pair. What does a lone pair do? It sort of pushes down those, yeah. So it makes the bond angles a bit less, makes it 107.5, doesn't it? Right. If in the case of oxygen, oxygen always forms 2 bond pairs, and it's got 2 lone pairs, one there, one there. So what does that do to the 107.5 bond angle? It makes it even smaller, which is usually quoted as like 104.5, isn't it? Right. And so we can see there that we have got one of those molecules has got an oxygen in it, and that's ethanol. Okay. And so ethanol, if you think about it, let's get rid of that. It's really, if that is just CH2, CH3. So that's going to have a bond angle like water of 104.5. So ethanol is going to be that one. All the other ones are all going to be 109.5, except for ethene, of course, that's got a double bond in it. So that's going to be 120 degrees, which is even bigger, isn't it? So we're doing the smallest one is ethanol. What's the systematic name for the compound below? Right, now we should look for the longest carbon chain. So let's do that. So we can number it this way: 1, 2, 3, 4, 5, 6. Well, let's do, okay, let's do the red numbering, do it the way around. So I had 1, 2, 3, 4, 5, 6. So it's going to be something hexane, isn't it? Hexene, little one. So it's got to have a hex in it. So you can see, first of all, C and D are not right because they have got pent as the longest chain. They're trying to trick you there into thinking. I just draw that. They're trying to trick you into thinking, oh, this is pent, like 1, 2, 3, 4, 5, and then call this an ethyl substituent. Well, that's not right to do that. You should always go for the longest carbon chain, which is 6. Okay, so it's got to be A or B. Right, and so should we use the blue numbering? If we use the blue numbering, we can see we've got the double one between 1 and 2, so that's going to be 1-ene. And the OH is on number 3, so that's 3-ol. And we've also got a methyl group on number 4, so it's going to be 4-methyl hex. So you can see B is the right answer. Why shouldn't we call it? Why shouldn't, if you use the red numbering, the red, you'd end up getting A, which would describe the molecule, right? But it's not the right answer because you've got higher numbers there than you need. You can always work out so you've got the lowest, use the lowest numbers. Okay, so B is the right answer there. Right, the dienes homologous series. What's this? What's the general formula of the dienes? Well, let's try to go for that one. So what's it going to be? It's going to be, I'm going to draw that out. It's going to be CH2 CH it's going to be CH2. So that's going to be C4H6. So so it's going to be Cn. Now, how do we get that? So that means it's going to be H 2 times 4, which is 8, minus 2 to get the 6 there. So that's going to be our answer there. Okay. Another way of thinking about that is if you've got an alkane, it's always going to be CnH2n plus 2. If you've got one double bond, then you lose 2 hydrogens, don't you? So if you've got 2 double bonds, you'd have to lose 2 more hydrogens, so it would be minus 2. C is the correct answer there. 19. Which statement about absorption of radiation is correct? Absorption of infrared radiation can break covalent bonds, forming radicals. No, infrared hasn't got high enough energy to do that. It can't do that. Okay, that's UV that does that. Absorption of IR causes covalent bonds to vibrate more. Well, that does, and that's why they absorb, infrared radiation. That's why we can see, look at the infrared spectrum of an organic molecule. It's absorbing infrared and making the bonds vibrate. Absorption of UV is a major cause of global warming. No, that's infrared, isn't it? Okay, and absorption of UV radiation is not used in modern breathalyzers. That's infrared, which we use that basically infrared spectroscopy of someone's breath. Okay, right, 20. Okay, this is addition polymerization. The repeat unit of the addition polymer is shown below. So how does that form? Well, when you form addition polymers, what happens? You have the monomer has got a double bond between those 2 carbons there, and those that. So that's what the monomer is going to look like. So it's going to be CH2 double bond CH2OH. When we draw that as a skeletal formula, it's going to look like that. Where's our double bond? And there is our OH. That's carbon number 1, number 2. That's carbon number 1. There's number 2, and there's our OH stuck onto it. So the correct answer is A. Important to realize that that is not a carbon there, is it? Okay, it's not a carbon. It's the OH. Yep. Right, so that's the end of the multiple choice section. I'm going to close down this whiteboard and open up a new one for the section B questions. Okay. Question is about atomic structure. Complete the table to show the maximum number of electrons that can occupy each shell. Okay, so first shell, you only have an s orbital in the first shell, don't you? How many s orbitals we've got? We've got 1, and you can fit 2 electrons in it. There's no p or d in the first shell. Okay. The second shell, right? You do have a p orbital. Right? You have 1 s orbital fits 2 electrons, and you have 3 p orbitals, don't you? Each one with 2 electrons, so that's going to be 6 there, and there's no d orbital. When you get to the third one, you've got the s and the p, and you've also got d orbitals. And how many of them you got? You've got 5, 2 electrons in each, so that's going to be 10. So if we add those up, we get 2, 8 in the second shell, and 18 in the third shell. Okay, selenium has atomic number 34, and we've got 2 isotopes, right? So Right, we've got to fill in the number of particles. Right, so they've both got 34 protons. That's what makes it selenium, isn't it? Having that number of protons. How do you work out the number of neutrons? Well, you subtract that's the mass number, take away the atomic number from the mass number. So 76 minus 34 gives us 42. And this one has got 6 more. It's 82, so that's going to be 48, isn't it? How many electrons? These are neutral atoms, so the same number of electrons as protons, so it's 34 electrons in each. See, relative atomic mass of an element can be determined from its mass spectrum. Okay, the table shows the results of mass spectrum of sulfur. Right, so now we've got to calculate the relative atomic mass. Well, how will we do that? Well, we have to say, right, you've got, in 100 atoms, you'd have 94.93, so you do 94.93 multiplied by, each one weighs 32. So it's easiest to divide it by 100, though, isn't it? So let's do, rather than the percentage, you use the abundance. So that's going to be equal to 0.9493 multiplied by 32. Right, plus divide 0.78 by 100, you get 0.0078. That's the abundance, not as a percentage. And each one weighs 33. And then finally, we have got the abundance of the 34S. So that's going to be 4.29 divided by 100. So it's going to be 0.042929 multiplied by 34. Do that lot on your calculator and you get 32.0936. But it does ask us to give it to 3 decimal places. So we should change that to 32.09 and round the 3 up to a 4. Okay. Okay, halothane, all right, is used as an anesthetic, and the systematic name is given there. Draw the structure of a halothane molecule. Right, so it's ethane. Let's draw 2 carbons. And we'll call that one number 1 and that one number 2. So 2 bromo, it's got a bromo on number 2, it's got a chloro on number 2, and it's got 3 fluorines on number 1. Okay, and then that means that there's got to be a hydrogen on that one. That's the structure. Right, what is the number of fluorine atoms in 7.96 grams of halothane? Well, it tells us here, to save a bit of time, tells us that the MR is 197.4. Okay, so we've got to find out the number of atoms. So we need to find out the number of moles and then multiply by Avogadro's. So what we're going to do, moles of halothane, that's going to be the mass over the MR. So that's going to be 7.896 divided by 197.4. And that works out to be exactly 0.04 moles of halothane. Now, in 1 mole of halothane, how many moles of fluorine atoms have we got? We've got 3 times that amount. So moles of fluorine, F atoms, is equal to 1 molecule contains 3 fluorine atoms, so times by 3. That gives us 0.12 moles. Now we need to work out the number of atoms, so we need to multiply by the Avogadro constant from the data book. So number of atoms is equal to the moles, 0.12, multiplied by the Avogadro constant, 6.02 times 10 to the 23. That gives us 7.224 times 10 to the 22. I should really leave it as 4 sig figs because that's what that's given to there, even though, well, it's a bit naughty really because the Avogadro constant is only given to 3 sig figs. So I think if you look in the mark scheme, it does let you have that, but I think it would be more correct to say 7.22 and round that down. Yep. Okay, question about enthalpy changes. Right, we've got this reaction for how hydrogen is manufactured from reacting methane and water together. And it is an endothermic reaction there, okay? The rate of this reaction increases with the catalyst. So you've got to complete the energy profile diagram. You've got to show the activation energy without and with a catalyst, and also the enthalpy change delta H. Now, it's important that delta H is positive, so there is more enthalpy in the products than in the reactants. In other words, heat energy has been taken in from the surroundings and turned into sort of chemical energy, so the products are going to be up here. So that line that's got to be higher than the reactant, so that's going to be 3H2 and carbon monoxide. All right, now what happens in energy profile? You're going to get something like that. Okay, that's without a catalyst. What's the activation? The activation energy is going to be that. All of that. That's EA. How does a catalyst work? Well, let's put in delta H first. So delta H is going to be that bit there, the difference between the reactants and the products. How does a catalyst work? It lowers the activation energy. It doesn't change delta H though. So we just have to draw with a catalyst. You're going to have a line which goes something like that. And what's the activation energy with the catalyst? Squeeze it in there. It would be all of that. So you can see the activation energy, EC, is lower than EA. Okay, explain how Le Chatelier's principle can be used to predict the conditions of pressure and temperature for maximum equilibrium yield. Okay, so 4 marks going for this. What does Le Chatelier say? Whatever you do to an equilibrium, it will try and oppose the changes. So what should you do? Look, it is an endothermic reaction. So how can you make that go forward? Well, you will increase the temperature, use high temperature. If you use high temperature, it will try and lower the temperature. How does it do that? How will it try and oppose that? By moving the endothermic direction. Right, now let's look at the pressure, okay? So on the left-hand side, we have got 1 mole of methane, 1 mole of water. So that's a total of 2 gas moles. And on the right-hand side, we've got 3 hydrogens and 1, so that's 4 gas moles there. So that means as it goes forwards, the number of gas moles increases. So you should use a low pressure, and that will make the reaction move in the direction of the most gas moles. Okay. Now it's only asking us about equilibrium here there, so you don't want to waste time by getting sidetracked saying, yeah, well, you might use a high pressure, yeah, to increase the rate of reaction, because it's not asking that. Right, your 4 marks are just for those points there. Okay, and here's a bond enthalpy calculation. The reaction for the production of hydrogen is repeated below. And the average bond enthalpy is right. So we've got to calculate the bond enthalpy of the HH bond. So I think when you do these, it's quite important to draw out the molecule so you can see the bonds. You don't forget about any bonds there. Okay. Now they tell us delta H for the reaction is that plus 206. Okay. So the way I like to do these is do a Hess's law cycle. And here we have got on the third thing in the cycle, we've got the gaseous atoms. So we've broken every single bond. Okay, and we've got atoms as single atoms as gases. Right, what on the red arrow, what have we done? We have broken we have broken, which is endothermic. Bond breaking is endothermic, so it's going to be positive. We've broken 4 times the 4 of the carbon hydrogen bonds, okay? And we've broken 2 in the water of the hydrogen oxygen, that's 464. If we add all that lot up together, we get we get 2,580, and that's plus because we're breaking those bonds. Now let's the green arrow. What we're doing there, we're making bonds, so this is going to be negative. So one of them we don't know. That's what we've got to find out. So let's call that x. The x, and I'm going to say minus 3x because when you make a bond, you get it's exothermic. You get the energy out, and we're going to make one of these carbon bonds in carbon monoxide, so that's minus 1077. So we can see then, we just do Hess's, apply Hess's law there. You can see, right, look at the blue, plus 206. Is equal to, well, we're following the red arrow, so we don't change the sign, so it's plus 2580. And this one is minus 1077. And we've also forming 3x there. Right, so let's just rearrange, get all that together. So we end up getting there 3x is equal to 206 minus 2580 plus 1077. So 3x, add all that, do that little bit, is minus 1297. So x is equal to 1297 over 3. And that gives us minus 432. The minus sign is because we are making the bond there, so it's exothermic. So our answer is 432 kilojoules per mole. Right, now that is about a little bit more than halfway through the paper, so I'm going to stop there and continue with that paper in the next video.